Hello, everyone, and welcome. My name is Cumrun Vafa, co-president of ColumbiaDC and a graduate of the School of Engineering and Applied Science. Now, first, let me thank our partners, Harvard and MIT clubs of Washington, D.C., and the members for being with us tonight. We are very privileged to have this evening Cumrun Vafa, professor of mathematics and natural philosophy at Harvard University, to talk about fundamental laws of the cosmos. This will be through puzzles, a subset of 100 or so puzzles in Professor Vafa's the highly acclaimed recent book with the same name, Puzzles to Unravel the Universe. So this will be a little more interactive than our usual webinar. So I would like to ask everybody to remain muted, but there will be a chance to ask questions and interact with your reaction buttons. I dare to say that there may be pop quizzes along the way. Let me briefly introduce our speaker before we move on. Professor Vafa is Hollis Professor of Mathematics and Natural Philosophy in the Physics Department at Harvard University, where he does his research and teaches theoretical physics since '85. He received his bachelor's in math and physics from MIT before moving to Princeton, where he completed his PhD in theoretical physics. Professor Vafa is world-renowned for his groundbreaking work in string theory and mathematical technology needed to explore the field. He's one of the founders of duality revolution in a string theory, which has reshaped our understanding of fundamental laws of the universe. Professor Vafa has received numerous prizes and recognitions for his work on theoretical physics, including 2017 Breakthrough Prize in Fundamental Physics, the 2008 D-Rock Medal of ICTP, and prizes for his work on mathematical physics from American Mathematical Society as well as the American Physical Society. Professor Vafa, it's all yours.
Thank you so much. It's a great pleasure to be here, and thanks for inviting me to give a talk here. I feel completely at home for three reasons. First of all, this is an event sponsored by Harvard Alumni Club, as well as the MIT, which I was an undergraduate at, and Columbia, where my son is getting his PhD currently. So I really feel completely at home here, and thanks for inviting me. And not to mention that I have so many relatives in Washington, D.C., I cannot count. So everything kind of hangs together for me. Anyhow, I'm very happy to give a talk here. Let me share my screen if I can. So I'm assuming that you can now see my screen. Is that the case?
Yes, we can see.
Okay, very good. So I'm going to talk about puzzles to unravel the universe. And this is related to a book that I just put out. Actually, I should say that the COVID period helped me finish the book, which was in a way I would not have gotten a chance to finish it this quickly. It is based on a course I have been teaching as a freshman seminar course at Harvard University for the past 9-10 years. And the idea for it is to use puzzles as a springboard to learn about fundamental laws of the universe. So math and physics have a beautiful history of interaction through many millennia. And you know, there's various highlights that one can mention. I mean, it goes all the way back to Greek mathematicians and philosophers that they were studying, for example, geometry and the elegance and the beauty of Platonic solids, for example, and they tried to attach physical meaning to these symmetric objects. Like the octahedron was a symbol of air, and the cube, and this basically the 5 elements that they thought nature is made of. They associated these elements with symmetric Platonic solids. So they were trying to find deep connections between physics and mathematics in a language that was not which was maybe ahead of time in some sense, because they really didn't have the right tools to try to do this, but they were striving for some connections there. This continued with the tradition for over many different centuries through many different cultures. For example, the cultures involving all the way back to Chinese, Indian, Islamic scientists. All these different cultures added a little, and one by one they gradually built up to the science that we know today. For example, the Biruni measured the radius of the Earth by a very simple idea. He thought that if you go on top of a mountain, and if you look at the horizon will not make a perpendicular angle with respect to the vertical line. And by that, finding that deficit angle alpha compared to the height of the mountain, he was able to estimate the radius of the Earth with very good accuracy. You might be surprised that by 11th century, the scientists had measured the height of the atmosphere. This is something that we think, because we send rockets into space and so on, we know all about the height of the atmosphere, but this was known 1,000 years ago, and they would know how to compute this height. And how do they do that? Well, very simple idea. They just said, if you're, let's say here at north here, and you have a sun which is setting, so as soon as the sun sets, you don't see the sun anymore, but the light above you is not, the sky above you is not quite dark, because the sun, even though it's set, it is still reaching, the sun rays are still reaching the atmosphere above you, until the sun is far enough down such that even the last ray reaches the top of your atmosphere. So after it crosses that point, then it cannot even illuminate the sky above you, and therefore it gets really dark. In other words, they had noticed that it takes a while from the sunset to the time the sky actually gets dark. And from that, they found estimation for the height of the atmosphere. Very simple idea, and it's just geometry. So at that time, basically, the main use of these were the use of geometry to try to get some measurements, like radius of the Earth, height of the atmosphere, and so forth. As we got closer to the modern times, things become more advanced. Newton used calculus to describe the laws of mechanics. He invented calculus, not just used it, but invented calculus to try to describe the laws of mechanics. And a century later, Gauss, mathematician, was studying aspects of non-Euclidean geometry and was beginning to ask whether our universe has these curved geometries, like geometries in which the straight lines, if you connect them, make angles which don't add up to 180 degrees. So these are the kind of non-Euclidean geometries that were beginning to come from the mathematical way of thinking, but not necessarily yet implemented in the physical theory. So thing continued, and it was continuing with the work of various people. For example, Maxwell studied the laws of electricity and magnetism, and he found that by incorporating the laws correctly, you find that electric and magnetic fields can move in a wave, and he basically estimated the speed of the wave to be the speed of light, and therefore he postulated that moving electric and magnetic waves is nothing but electromagnetic waves. Quite a remarkable discovery that he made. Riemann, again a mathematician, tried to use Riemannian geometry to try to unify electric magnetic phenomena and gravitational force using the curved spaces. But he didn't have quite the right tools, and that had to wait till Einstein came along. And he used the Riemannian geometry not in three-dimensional space, but in three-dimensional space and one time to unify a lot of physics, and in particular give a geometric meaning to gravitational force. So, according to Einstein's theory, the matter created a curvature in the fabric of space and time, and that caused the objects to go in orbits around each other. Now, Kaluza and Klein, using Einstein's theory, extending it from 3 spatial directions to 4 spatial directions by adding a little circle over every point. So Kaluza and Klein assume that every point in space has a tiny little circle, which is so small we cannot see it. And in this way, they managed to unify electricity and magnetism with Einstein's theory of gravity. And so it gave a beautiful unified theory for all of it. Now I come to my area of research. And my area of research is a field called string theory. The aim of string theory is to unify fundamental forces and particles into one framework. It aims to describe physics from the smallest possible scale, a trillionth of a trillionth of the size of an atom, all the way to the size of the universe. And the basic postulates for this theory is that the fundamental particles are not point-like, but extended objects like strings. So we think about particles not like point-like objects. For example, here I'm depicting 3 quarks, which make up a proton. These 3 quarks should be viewed not as particles, but as little strings, little vibrating loops of energy, which we call strings. And they form that's the way we should think about them if you want to connect, if you want to resolve the inconsistency between quantum theory, which is the theory describing the smallest parts of the matter like atoms, and gravity, which is very good for large distances. If you want to combine these together, it turns out that you have to replace point particles by string-like or extended objects like strings. And the interaction between these particles are replaced by splitting and joining of strings. For example, here I'm showing as time evolves, 2 strings come and join and make 1 string. As you can see, this forms a surface. The movement of the string forms a surface, and this surface is called the pair of pants diagram because it looks like a pair of pants. And this turns out to be the fundamental way that all the forces gets unified in string theory, just like this simple diagram. So it's a very elegant, minimal geometric theory describing all particles and all forces. And all the different particles like electrons and quarks and all that correspond to different vibrational modes of the same string. So it's unified into one object. So it's very elegant. This area is very mathematical, and it involves many abstract ideas. For example, the dimension of space is more than 3 spatial dimensions at one time. In fact, it is 9 spatial dimensions at one time.
Yeah.
The shape and size of these other tiny 6 dimensions affect what we see. Of course, these 6 extra dimensions better be tiny, because if they weren't tiny, you could ask, where are they? And so if they are tiny, it'd be hard to detect them with our everyday experiment because they're too small to detect, too small to discern with the experimental apparatus available with the current technology. So they're assumed to be tiny. Strings wrapped around these tiny dimensions lead to insights about how black holes work, how the beginning of the universe looks like, etc. So they have very nice properties, and they have led to many insights into physics. For example, we have found that the degrees of freedom of black holes, which Hawking had predicted, are hidden as strings in these extra dimensions. So there are these properties that these extra dimensions are useful for. So you can think about these extra dimensions as these little compact spaces or spheres at every point in the 3 spatial directions. So at every point, like where you are, there'll be one sphere. Where I am, there's another sphere, and so on. And at every point, there's a sphere, or more complicated 6-dimensional geometry. Okay, this was just a brief introduction for my work, but that's not what I'm going to try to do in more detail in this talk. My aim is different. My aim is, in fact, to show you the opposite. That is, I want to show you that the highly mathematical aspects of string theory, which is typical of many attempts to connect physics with reality, can actually be illustrated by simpler ideas. So these deep physical ideas have simple mathematical underpinning, and not only that, but they can be illustrated by simple puzzles. So viewing these laws as illustrated by puzzles gives us a way to kind of internalize what these laws mean in practical terms. In other words, we can dirty our hand by actually solving a puzzle and see what these puzzles actually mean, and therefore how do you interpret these complicated physical laws in ways that are more familiar to us. And of course, puzzles are fun in their own right, which is another reason we would like to perhaps illustrate them by examples. So I'm going to illustrate this math-physics connection through various topics. I'm going to go one topic by another, but I kind of need your help. I need your help because I want you to solve the puzzles. So you're going to help me solve the puzzles. Now, so many of these puzzles are going to be answering like yes, no, or something. And so I'm going to ask you, what do you think? How many think yes or no? And I will maybe, if you can, probably the easiest way is that those who are willing to have their video on would basically raise their hands, or if they're okay with that, answering yes or no. And if you're not okay, that's fine too. But it would be fun to have interaction that way, perhaps. So please feel free to turn on your video if you feel comfortable, and then we can answer these questions. That'll be more fun. During the COVID, there are a few things we can do interactively, so maybe this gives you a way to actually do something together, and that would be another reason to do it. Anyhow, wonderful. Thank you. Okay, so let's start. So the first topic I want to illustrate is symmetry and conservation laws. What is the meaning and role of symmetries, and why does it have to do with conservation laws? So here, I want to describe this puzzle. We have two containers, one in green paint, one in white. We take a cup, fill it with green paint, pour it into the white paint container, and stir it. And after we stir it, we take the same amount from the mixture, the same amount of liquid, and pour it back into the green container, and then stir this. Okay, so let me just tell you what we were doing. We started with two equal size containers containing green and white paint, respectively. We poured paint from green to white, mixed it, and then from the mixture, we took the same amount of liquid and poured it back into the green container. The question is this: after we did this, does the green container have more white in it, or the white container has more green mixed with it? Is the question clear? So those who think that the green has more white in it, please raise your hand. Those who think that the white has more green in it, please raise your hand. Those who think they are equal, please raise your hand.
I think the green.
Okay, so I would think that maybe the majority of you thought that the white has more green in it. And this is the answer that most people actually give. And the reason for that, perhaps, is the following. You see, when you originally took from the green container and put it into white, you were putting pure green. But when you're taking back from the mixture, you are bringing back some of the green back to the green container. So therefore, it stands to reason to think that the white has more green in it. And so that's what most people would think, and that's something natural. However, I will not convince you using symmetry arguments and conservation of mass that they actually are equal admixtures. How does that work? Well, to begin with, we have equal volume of green and white paints. At the end, since we took the same amount of volume, just think about the volume of the liquid of paints, final volume is also equal between them, right? Mm-hmm. So then think about symmetry between the left and the right containers. On the left, you start with the same amount of volume, and you ended up with the same amount of volume at the end. But some of the green is missing. Where is that green? Well, it must be in the white. In the white container, you have the total volume, which is the same as the green volume, and there's some white missing. It must be the same thing as occupying the green. Therefore, they're equal in volume. So symmetry immediately tells you they are equal. And so, in fact, you can think about unmixing them. If you unmix it, of course, the same layers that is in one, it should be in the other if you exchange them. And of course, they should be equal in amount because the total volume by symmetry is the same. And so that shows that their volumes of mixtures are the same. And this deconfuses us. A simple symmetry reasoning and conservation of the total volume in this case tells us that we were fooled by the procedure. So physicists love these kind of symmetry arguments because it cleans and clears up our mind with a simple way of thinking, which illustrates the mistakes we could be making. So it might have sounded boring if you hadn't seen the puzzle, perhaps, that there is this powerful application of this simple idea of symmetry. Okay, this can also be illustrated by a deck of cards. Suppose you have 10 red and 10 black cards. You take 3 of the red and put it in the black, among the black 10 cards, and mix them. And then you do the, out of this mixture, you take 3 of these cards and put it into this, and you mix it. And then you ask, does the 10 cards that you're left with have more black in it, or the 10, which one has more black or red, has a mixture of the other one? And of course, the answer is that they have equal amount. The reason is whatever is missing from one must be in the other, because you had 10 red cards to begin with. So if you're missing 2 red cards, it must be here, and that must be the same amount of black cards you're missing. This is the same version of that paint puzzle in terms of, concretely, in terms of counting. Now, I want to give you more examples of symmetries. And so let me go back all the way to Aristotle, who was talking about something which he thought was obvious. He believed that heavier objects fall faster than lighter objects. If you forget about the air resistance or anything like that, heavier objects fall faster than lighter objects. Galileo, by experiment, convinced himself that all objects fall at the same rate. He famously went on top of the Pisa Tower, it said, and he dropped big and smaller stones, and they all fell at the same time when he dropped them at the same time from the same height. Now, at that time, there was actually, I do see two hands raised. I guess, do people want to ask questions now? Sure, please go ahead if you want to ask questions. Can you unmute yourself? Is that how it goes? I see questions, hands being raised. Please go ahead, ask your questions if you have questions. Bob, do you have a question? I guess your hand is raised. No? Okay, maybe it's by mistake.
I think that's left over from your question before.
Oh, sorry. Okay, sorry. Oh, raise hand. I see. No, you literally. Sorry. Okay. So you're smarter than I am. You just imagine the more technologically correct answer of raising hands. You assume. Yes, that's another way of answering it. I see. I was literally meaning I can see your hands, but you're right. You could of course do the raise hands in the usual method. So people who don't want to turn on their video, they can use their hands that way. That's fine. So Galileo tried to convince people why objects fall at the same rate. He said, well, do the experiment. But believe it or not, at that time, science was not an experimental field. They wanted to understand why. So they told us, you have to convince us. It's not enough just to, you have to dirty your hands to do an experiment. You have to actually explain why is it that heavier and lighter objects fall at the same rate. So he had to come up with an argument to convince them. And he came up with the most brilliant idea using symmetries. And this is how he reasoned. He said, suppose you have 3 bricks of the same size, same mass. And you hold these 3 bricks at the same height above the ground and release all 3 at the same time. Which one will fall first? Which one will hit the ground first? That was the question. What do you think is the answer? Well, by symmetry, they should fall at the same time because they're same size, same shape, everything is the same, and they're the same height. So by symmetry reason, by translation along the horizontal plane, which is the symmetry of this problem, they should fall at the same rate. And indeed, it is the case. So for example, here, I'm just showing you this 3 bricks being dropped from the same height. They hit the ground at the same time. Okay. Next, he asked, suppose you take 2 of these bricks and bring them closer or farther from each other, but don't change the height. Does it change who falls first? Well, the answer is no, because the symmetry is translational symmetry doesn't have, in the horizontal direction, there's a translational symmetry. They still fall at the same rate. It's obvious, you say. You say these are obvious. What does that have to do with what our question was? Well, Move them in horizontal direction any way you want, right? It shouldn't matter, right? It doesn't matter. So let's continue. Continue moving them horizontal direction and touch the two of them together and drop. Do they fall at the same time? Yes, sure, it doesn't matter. They're the same height. But then he made the brilliant observation and said, aha, this now is twice made of 2 bricks. It's twice more massive than this other one. And you just told me they fall at the same rate. So therefore, more massive objects and lighter objects hit the ground at the same time by symmetry reason. So he, in this way, deconfused the mind about heavier objects falling faster is incorrect. Again, by appealing to our sense of symmetry. Quite brilliant argument. Physicists love this kind of argument. This is called, well, this is an actual experiment, but you can also call similar experiments what we call thought experiments. You don't have to do it. You kind of think about it, and it's kind of clear what the answer is. Now, I have told you about the power of symmetry, but it turns out symmetry breaking is even more fun, but not breaking by hand, but what we call spontaneous symmetry breaking. So let me illustrate this by a puzzle. We have 4 towns, A, B, C, and D, on the 4 corners of a square. We want to connect these 4 cities through a highway system, and the highway costs money. And the more the length of the total length of the highway, the more cost it's going to be making. So therefore, we have to make this total length of the highway as short as possible. The question is, what is the total? How do you design the highway to have a total length minimal, but yet allows you to get from any city to any other city? Now, each highway, each road that you're constructing is you can go either way, back and forth, so that's not an issue. And you don't have to directly go from every city to every other city, as long as you can get from any city to any other city through some path in this highway, you're fine. So what is the shortest total highway system you can design? I'll give you a minute or shorter just to think about what you think is the best design. Put your engineering designer hat on, please. And now I'm going to ask you a question. How many of you think this is the answer for the shortest path? Please raise your hand if you think this is the shortest.
But that doesn't mean B can get to D.
Sorry?
I didn't hear the question.
I thought all of them had to get to all of them.
Yeah, so for example, here A gets to B through getting through this circle, like through this intersection.
Okay.
Okay. Okay, this is one possibility. How many of you think this is the best?
Send me outside that one.
How many of you think this is the best possibility? Raise your hand. Okay, not many of you think, yeah, of course, this sounds a little bit strange because even if you remove one road, you still can go from every other to every other. How many of you think this is the best possibility?
Mm.
No? You? Well, of course, you can move this road from there to any place, and that doesn't change the total length. But actually, this is not the answer either. How many of you think this is the answer?
Never really thought of that.
This turns out to be the answer. It looks strange. It is not symmetric. Well, you have to come to make a highway which is 120-degree angle. These roads make not a 90-degree or anything, 120-degree angle. You go this way, and then you connect them and make. So these 3 angles are equal, and each are 120 degrees. This is the shortest total length. Now, you're puzzled. Many people are puzzled when they see this solution. Why? Because it doesn't respect all the symmetries of the square. For example, suppose you want to go from the town A to town B versus from town A to town C. It is shorter to get from A to C because you just go directly from here to here. But if you want to go from A to B, you have to go this extra length. So A to B is farther away than A to C, even though the physical distance from A to B and A to C are equal because they were on the 4 sides of the square, 4 corners of the square. So therefore, you have broken the symmetry. Well, we didn't break it by hand. These cities were on the square. I just asked you to solve it by finding the shortest highway system. So the highway, the minimal, shortest highway system broke the symmetry. Of course, you could have designed this so that A and B get closer like the other way and then come down here and then connect C and D. But no matter which one of these two options you choose, you have broken the symmetry of the square. So either way, symmetries of the square are broken. This is a spontaneous symmetry breaking. And you might say, okay, so what does it have to do with physics? Well, actually, it has a lot to do with physics. And I'm going to give you some more examples of how symmetry breaking have to do with physics. Early Greek philosophers had already figured out that the Earth is round. They had in fact estimated the radius of the Earth by studying the shadow of a stick at noon. And from that, you can actually discover the radius of the Earth by looking at the shadow as a function of the height, how much away you are from the equator. So they had already been very smart and figured out that the Earth is round. And then they were noticing that the Earth doesn't move. I mean, look around you, the Earth does not seem to move. That's what they thought, at least. They thought the Earth is not moving. And they wanted to explain why Earth isn't moving. So they said, you know, Earth is a sphere, and it's a center of the whole universe. Now, if it were to move, it breaks the symmetry. What symmetry does it break? Well, it has to pick a direction. Just the very fact of picking a direction is arbitrary, and you break that spherical symmetry. So they said that if you go in some direction, if Earth were to move, it had to move in some direction, and that direction, which one is the preferred direction? There is no preferred direction, therefore it doesn't move. In other words, since the movement itself breaks the symmetry, it cannot happen, and therefore Earth is not moving because of symmetry. This is what their argument was. But actually, not all the philosophers, Greek philosophers, agreed. In particular, Aristotle did not agree. He said this is not a good argument. And the way he reasoned is the following. He said, suppose I put you at the center of a circle, and I put food around you in a circle, equally this far from you. You're at the center of a circle, and the food, like loaves of bread, are symmetrically located around the circle. Okay, now he asked, are you going to stay at the center of the circle forever because it's a symmetric point? He said, no way, you're going to starve. So therefore, you don't care if you break the symmetry. You're going to go and grab that loaf of bread. So you break the symmetry. So being at the more symmetric point is not the preferred situation. So he reasoned out that this is not a good argument. Symmetries can be spontaneously broken if they are not advantageous to us. So he said the same reasoning for the Earth. He could not accept that that's necessarily the right argument. It could be that the Earth doesn't want to be at that symmetric point. So in fact, your bodies reflect that. Spontaneous symmetry breaking is imprinted on our bodies. Why is that? Well, we live on Earth, which is by and large is symmetric under rotation on a horizontal plane. So if you rotate by 360 degrees all around you, on the average, they look all the same, but your eyes are not symmetrically around your head. Your eyes are only in the front. So your body is not symmetric under rotation, on horizontal rotation. It's approximately symmetric under reflection, but even that's not exact. But certainly it doesn't have rotational symmetry. And so your body has broken that symmetry. Why is it broken? Well, because evolution has decided it is more economical for your body to use its resources and have only two eyes in the front. It doesn't need all the eyes around. Why is that, you might think? Well, maybe one reason could be that if you're in the middle of a circle, and if you have bread around you, you want to go towards the loaf of bread, so you need your eye to guide you where it is and go and get it. So therefore, having eyes all around you may not be as useful as having eyes in front. At any rate, this is an explanation possibly of why spontaneous symmetry breaking is crucial in nature. In fact, more than that, it turns out that modern applications of symmetry breaking has been the discovery of the Higgs particle and the origin of mass. So you see, the modern explanation of how you and I and everything gets its mass is the following. there is a field which is like akin to having a potential and having a particle like on top of the hill. And if the particle rolls down, it leads to giving mass to particles, and the mass of every particle is proportional to how far away this ball is from the center of the circle. So if it were to stay on the top of that hill, then it would have been no mass because the distance to the center would be 0. But of course, that's not the preferred position because a tiny little jiggle there will throw it one way or another around farther down because the valley would have lower energy. And so it will go down at the bottom of the valley. And this turns out to be the solution of solving of the way we get mass through this what's called the Higgs mechanism. So this is spontaneous symmetry breaking. Okay. Here I want to illustrate unreasonable power of simple mathematics. Now, you might think, you know, to do really cool stuff with math, you really have to know fancy math. So in the college, we saw that that's what is needed, seems to be needed for fancy problems. We need to know at least calculus and maybe other stuff. But here I want to convince you that's not necessarily the case. So here it is. Consider Earth on the equator. So here we have a blue Earth, and this white represents an equator. And imagine you wrap a belt around the equator. And you open up the belt. So you have a belt the same length as the perimeter of the equator. And what we want to do is we add 1 meter to it. So of course, this equator is huge, and you added 1 extra meter to it. And what we do next is we wrap it around the Earth. And the question we want to ask is how much does this belt rise above the Earth? In other words, what is this x? Now, I know you can calculate this. Please don't calculate it. I want to just use intuition. So how many of you think that this length x is such that you can move, let's see, a piece of paper under it? Raise your hand. How many of you think it's big enough for it to, you can, a mouse can go underneath? Raise your hand. Okay, wow, okay. How many think you can put a skyscraper underneath? Okay, nobody says skyscraper. Okay, okay. Yes, yes. Okay, so I just want to see if everybody's awake. Yes, so no skyscraper, but some of you said piece of paper, and some of you said that even you can perhaps a mouse can pass under it. In fact, yes, a mouse can, unless it's really big. Namely, if you just look at the total circumference of the equator, it's 2 pi times the radius of the Earth. That's just a simple math, elementary school math, the circumference of the circle. And then you added 1 meter, so that's now the total length of the belt, 2 pi r plus 1. And that should be 2 pi times the new radius of the circle. The radius of the circle is r plus this extra amount x. So 2 pi r plus 1 is 2 pi times r plus x. So you can cancel 2 pi r's from both sides of this equation, and you learn 1 is equal to 2 pi x. Or x is 1 over 2 pi, or 0.16 meters, about 16 centimeters. So indeed, 16 centimeters is tall enough for a mouse to go underneath. Okay, so you see, this is, many people actually originally think that this is not going to work, because you would think that you just added 1 meter to this huge belt, so minuscule change to the total length compared to its length. And so you might think that it doesn't raise that belt much above the ground. So even many people don't think it's like as big as 16 centimeters. Now, however, there's another way you can ask this question. Suppose I pull the belt in such a way that it is tight on one side of the equator, and so it's asymmetric, and you pull it more on one side. Then you can make x bigger, right? How many of you think you can make x as big as 75 centimeters? Raise your hand. How many of you think you can make X 1 meter? Raise your hand. Yeah, nobody raised the hand for 1 meter. How many of you think you can raise it for 100 meters or more? Raise your hand. Well, I have one courageous person thinks you can raise it, or 2 people thinking you can raise it more than 100 meters. Actually, they are right. It turns out that you can raise it 121 meters. And this is completely outrageous from the, I mean, if you think of it. We added only 1 meter to the length of the circle, and if you pull it asymmetrically on one side more, it turns out you can lift it to 121 meters. How do you see this? Well, this one needs a little calculus. I'm not going to show it to you, but if you're up for it, and if you remember some of your calculus, please go ahead and check it out. But anyhow, here I want to say that math deconfuses us sometimes. We have to work at it and see how it deconfuses. One of the amazing, powerful things in mathematics is power of continuity. Functions are continuous. Also in physics, the laws of physics are continuous. So things vary smoothly and continuously from one place to the other. They don't jump up and down, they just gradually change. That's one of the basic properties of physics. Nothing is abrupt. So let me illustrate it by some math puzzles. Let's again go back to the Earth and the equator. Suppose we measure the temperature of the Earth on the equator as we go around the equator. Temperature generally varies around the equator, but it varies continuously across the equator. It just doesn't jump up and down. If you go to from one point to a nearby point, the temperature changes a little bit, it doesn't jump suddenly. So you have a continuous function of temperature as you go around the equator. But temperature can vary quite a bit across the equator as you go from one side to another. Is it possible that at any moment, there always are 2 points on the equator across from one another from the center of the Earth, which have exactly the same temperature? Of course, there could be some points like this. My question is whether there always are at least 2 points with this property, that are there, no matter what is the temperature across the equator, is it possible that always you can find 2 points, this point and the other point on the equator, which is opposite across relative to the center of the Earth, which have exactly the same temperature? How many of you think this is always possible? Raise your hand. How many of you think it's not possible? Raise your hand. Okay, so some think it's possible, some don't think it's possible. It turns out that by continuity, we now see that it's always possible to find 2 points which have exactly the same temperature, which are opposite relative to the center of mass from one another. To see that, consider 2 opposite points I denote by theta and minus theta. And if the temperatures are equal, of course, it's fine, we're done. But suppose they are not equal, we consider the difference of temperatures between these 2 points. T at theta minus the temperature at minus theta. Let me call this difference f of theta. So this function has a property that if you go from one point to the opposite point, it flips sign. In other words, if I go from theta to minus theta, if I go from this point to the opposite point, it changes sign, because if this temperature is higher than this temperature by some amount, it means this temperature is lower than this one by the same amount, and that's this meaning of that sign. So the function goes from whatever it was to minus itself as I traverse from one point to the opposite point. Now, when would I have the same temperature? Well, when f is 0. If f is 0 somewhere, if there is a theta for which f is 0, the temperature of these 2 points are the same. Well, suppose you start with some point theta where f is not 0. Let's say f is negative. If you go all the way down, if you go around by pi to the opposite point, we know f flips sign to minus itself. So whatever it was, at the end it becomes minus itself. But this function is a continuous function because temperature varies continuously. Therefore, if something goes from negative to positive, somewhere it's going to cross 0. And wherever it crosses 0, that's going to be where the temperatures are equal. So just by this simple continuity argument, you learn some topological facts, some basic facts about the equality of temperature in opposite points. In fact, you can use a slightly more sophisticated argument to show that at any moment, there are 2 points on the globe which are opposite relative to the center of the Earth, which have not only the same temperature, but also the same pressure. It's remarkable when you think about it. There are always 2 points at least which have this property. And it's not an amazing fact of physics other than the fact that temperature and pressure are continuous functions. That's all. They vary continuously. So now I talk about gravitational lensing. And this is another example of power of continuity. So Einstein described the geometry of space and time, the fabric of space and time, as is curved by matter. So if you have some galaxy somewhere, it could curve the space around it. And so if you have another farther away galaxy, when the light of that galaxy is trying to reach us here in the Earth, it passes through different paths. Even though it might go through different paths, it might still come back to Earth because the curvature of the space bends the light. So there's the bending of the light. And you could be seeing the same galaxy in 2 different directions. So if you're on the Earth, if you look this way, if you look this way, we go back. If you look this way or that way, you see the same galaxy. So you might be confused and say, oh, I have 2 galaxies. One is that way, one is over there. But actually, they are the same galaxy because that light of that same galaxy is reaching you. So by the time you're on Earth, even though you perceive the light that's coming from different directions, they're actually the same galaxy. So you get multiple images of the same object in this way. Sometimes, not always, sometimes. So for example, here, if you look at this, this piece of the sky, look at this picture here. You might think there are various objects here. Indeed, surprisingly, there are the objects that are here, some of them are repetitive. The blue circles here are the same quasar. And the 3 oranges are the same galaxy. So you see 5 pictures of the same quasar and 3 pictures of the same galaxy. Quite remarkable. Now,
and because of the time and because of the curve, you're also seeing them at different points in time. Is that right?
Well, yes, that's absolutely correct. Absolutely correct. But in other words, the light doesn't necessarily get you at the same time because they go different paths. Absolutely correct. Probably not too different, but yes, slightly different. Now, it turns out that you see here that there are odd number of images, 3. If there was no bending or anything, you get just 1 image. That's the typical situation. But here you see sometimes 3, sometimes 5. It turns out that you always get odd number of images. It's always, if there are no images blocked, of course you can have a light ray being blocked by some obstacle. Suppose the rays don't get blocked. If there's no blocking of the light ray, the number of gravitational images is always odd, and just less than half of them are inverted images. So if you have, for example, 1 image, that's just the right side up, no problem. If you have 3 images, the 3 images have a reflection. It's not the same images. 2 of them are the same side, same direction. 1 of them is reflected. And if you have 5 images, 3 of them are of the same side, but 2 of them are inverted. Just less than half of the images are always inverted. Now you might say, wow, how do we see this? This must be a very difficult fact following from Einstein's equations. Actually, it turns out it follows from simple continuity. Similar to what I told you about the temperature and pressure, well, a little bit more sophisticated. I'll try to illustrate this. This thing I'm going to do now is a bit difficult to understand. So I don't expect you'll be able to follow because it needs some preparations, some math preparation to see it, but I will try to explain it. So if you don't quite get the whole description, just it's understandable. It's a bit too quick an argument for this 1 hour talk, but I just want to illustrate that some simple math ideas can give you such amazing physical predictions. So the idea would be that if you look at a star, and this is the Earth, and if you look at the rays that's coming towards you, it is best to do the following. You take a sphere near the star, and another sphere, again, whose center is the same star, but closer to where we are. And you trace what happens to light rays. So if there's nothing between them, the light rays go straight. So every point on this sphere gets mapped to another point on this sphere. So this point goes to that point, this point goes to that point, this point goes to that point, etc. In other words, the light ray itself is like a map from a point on one sphere to a point on the other sphere. So in mathematical terminology, we say we get a map from this two sphere for the sphere near the circle, near the star, to the two sphere which passes by the Earth. What is this map? Well, this map takes every point on this first sphere and maps it to the same point on that same sphere, on the other sphere. So there's this map, we call it identity map. This is when there is no matter between us, between the star and us. Mathematicians define what's called the degree of a map, which is the net number of pre-images of a given point. So you take a point on the second sphere and ask how many points from the first sphere got to that second point. And it turns out if you count them by the orientation reversal or not, with plus and minus signs, is what they call the degree of a map. It turns out the degree of a map is something that cannot be changed. The degree of a map is something which is by continuity, you cannot change it. Now, if there is no matter between us and the star, the degree is 1 because it's the identity map. Every pre-image has one pre-image. But if you put more matter, the degree cannot change. Well, how can you get more images? Well, you can get 3 images as long as you have 2 of them which are orientation preserving, which gives you a plus sign, and 1 which is minus sign. So you get a plus, and a minus 1. You get 2, minus 1, which is 1. But if you have 5 images, you get the plus, minus, minus. So you get 3 minus 2. Again, it's 1. So continuity gives you that. And to kind of see that's a bit difficult to see it perhaps in a quick lecture like this, but let me just illustrate it by this visual. It's kind of like this. So you can think about the original sphere like kind of a distorted sphere, and the sphere that we are at is over here, and you look at the pre-images and look at which ones they're getting from, and here you can see different possibilities. So if the Earth is here, you see, for example, that there is 1 pre-image over here. And it's right side up because it's the same direction as you go here is the same direction as the Earth is going. If you go over here, there are 3 pre-images. And one of them is going in the same direction, but one is the opposite and one is the same. So plus, minus, plus. Over here, you get 5 images, plus, and 2 of them are minus. And yeah, so this is a topological way of seeing it. Now, mathematical abstraction is also very important in physics. We have to be able to abstract from what we see. And why is this important? Why is this useful? I will give it in terms of a puzzle. Here we have 4 ants. These 4 ants are moving on a plane, and they're going at constant velocity, but in different directions. All 4 are going in different directions. All the ants, not only their paths cross, but actually cross and hit at the same time. The question is, if all pairs of ants do this, except for possibly for one last pair, do we know if the last pair of ants must collide or it's not known? Is the question clear? So let me go back again, if I can. So we have 4 ants, ant 1, 2, 3, 4. They're going in 4 different directions with some speed. The speed is not changing for each one, but they might have different speeds. And all pairs of ants cross except ant number 1 and ant number 2, where we don't know if they're going to collide or not. Do they necessarily collide? Okay. How many of you think they would necessarily collide? Raise your hand. How many don't think it's necessary that they collide? Raise your hand. Okay. Very good. So we have answers in both directions. Let's see. To see the answer to this puzzle, it turns out we have to go to 3 dimensions. We have to bring in time. You see, we have to combine the space and time into one object, just like Einstein did. We have to abstract from this space-time. Why is that useful? Well, if you bring in time, each ant which is moving on the space at constant speed, and if you look at where it is at a given time, if you bring a vertical axis and call it the time, you will see that the ant is going on a straight line in 3 dimensions. The 3 dimensions made of 2-dimensional plane and 1-dimensional height, which is the time, because it's going at constant speed. So when we say out of these 4 ants, each one of the ants give you a line. So you have 4 lines in 3 dimensions. Now we are saying that all pairs of ants except possibly one collide, which means when they pass through the same point at the same time, it means these lines cross each other because that happens at the same time. So you have 4 lines in 3 dimensions, pairwise they cross each other. And the question is, would the last pair also have to cross or not? And this is now simple Euclidean geometry now. And you can see that it does actually, so let's explain why. So here, these are the ants. I have put an extra axis, which is the time axis. You see the ants cross, so this is the 2 and the 3 and the 4 form a plane. 1 and a 3 and a 4 form a plane. And therefore, this last one, since you have a line 1 and line 2 are both on the same plane, they better cross because they're going in different directions. So by arguing that this line 1 and line 2, both of them are shared on the same plane, that implies that they will cross. So it's a simple fact of Euclidean geometry. Okay. Now, the next thing I want to talk about is one of the most amazing discoveries that we have learned in string theory. Is called duality. Duality is the statement that 2 physical systems, which look so different that you cannot possibly imagine they are the same, they may nevertheless exhibit identical physical properties. So in other words, they can fool us to think they are different, but they're actually the same. It is very strange that this happens so often in physics, and we don't know why. We just have seen that's true. And that's one of the major discoveries in string theory, is the appearance of these dualities. It is somewhat like this drawing of Escher. You see, if you look at different corners of this drawing, different thing is going on. So if I told you, look at the left upper corner here, you see a white sky and the blackbird flying to the left. If you look at the right corner, you see, no, it's not about the white sky. It's not the day sky, it's the night sky and the white birds flying to the right. And if you go down here, you say, oh, it's not about birds or sky at all. It's about fields, black and white fields. And what is interesting is that these objects gradually morph seamlessly from one side to the other. For example, the sky gradually becomes the bird here, and the sky over here gradually becomes the bird here. And if you go up and down, they become the fields in a very gradual, seamless way. So there's this duality transformations, and this whole drawing fits together. So if I told you, look at this drawing, what is this a drawing of? You might say, well, it's day, or somebody might say, no, it's night, or somebody say, no, it's about fields, and so on. They're all right, because they're different aspects of the same drawing they're emphasizing, and they're connected together in one coherent fashion. And this is the kind of thing we see in physics again and again, these dualities. So here I want to illustrate it with a puzzle. Oh, before I start this, let me just go back. Let me try to see if I can pause it. So here we have a 1 meter stick with ants on it, and the ants are moving on it. So it's 100 centimeters, and each ant is moving at the same speed, 1 centimeters per second. The meter stick is 100 centimeters, and each ant is moving 1 centimeter per second. The ants are moving either to the right or to the left. If 2 ants come and collide, they reverse direction and continue going the opposite direction with the same speed, 1 centimeter per second, until they meet the next ant, and then they collide, and then they go again back. They change direction again. Each time they collide, they reverse directions until they get to the end of the meter stick. And when they get to the end of the meter stick, they just fall off. And what we want to do is to make sure to have ants lasting as long as possible on the meter stick. We want the last ant to fall the latest time, as late as possible. So, oops. So here, let me just illustrate here. You just see these ants colliding. You see this orange and so on. They're colliding, and then they fall down here. So we have 20 ants. And where do you put the ants? And which directions should they initially move so as to maximize the time the last ant is on the meter stick? How many of you think that we should put most of the ants near the center of the meter stick? Raise your hands. Okay. How many of you think half of the ants should go to the left and half should go to the right? Raise your hand. How many of you think it's okay to have all the ants moving in the same direction to get the one going the longest possible way? Raise your hand. How many of you think it doesn't matter where you put all the ants except for one ant? Raise your hand. Okay. Okay, well, it turns out that the answer is the last one, that it does not matter where you put every ant. The only thing matters is where you put one ant. And why is that? Well, this is because of duality transformation. How do you see this? What do I mean? Well, let me color these ants black. When these ants collide, suppose you have two of these ants collide and they go the other direction. If you don't care about the identity of the ant, how does it look like? Well, it looks like they crossed, they collided and went back. But no, suppose you just cross and go through each other. Do you notice any difference? No. If you don't care about the identity of the ant, whether they went through each other or whether they collided and went backwards, doesn't make any difference as far as where the total ants are, where they are located. So if you color all the ants black, you'll see this much better. So let's do it. Here we have colored all the ants black, and you would think that the ants are just going through each other. They don't care about each other. So you're just, by this duality transformation, you're changing the identity of the ants when they cross each other. And so all you have to do is to put one ant on the, let's say on the left, and tell it to go to the right, and it doesn't matter where everywhere else, what everybody else is doing. It's quite simple, and it's the picture of the duality that solves the problem. Finally, this is my last puzzle, and it's probably my favorite puzzle. It's a reflection on scientific methodology. It is something that we strive to explain to our students. What is science all about? What do we do? How do we come up with new ideas in science? Well, this is how we explain it to them. We say, well, we have examples. These are what, like experiments. Based on experiments or examples, we formulate a general principle based on these. And then after we come up with these principles, try to make them more intuitive, come up with arguments, why or how these work. And of course, we never stop experimenting and doing more examples. This is the basic scientific methodology, and I want to illustrate it by discovering, together with your help, some of the laws of circles. So we are going to learn something about circles, or we're going to discover it. So this is the problem. We have a circle, and we pick points on the circle. Here we just pick 2 points, and we connect the 2 points together. How many regions do we get inside the circle? Well, clearly we get 2 regions. So if you have 2 points, and if you connect them with a line, you get 2 regions. Okay, good. Suppose instead you have 3 points. Well, before I do that, so 2 points gives you 2 regions. Now, suppose you have 3 points. You add 1 more point here and connect all of the points together now. So now you have 3 lines. And now count how many regions do we have? Well, here we have 4 regions. 1, 2, 3, 4. So we learn if you add 2 points, you get 2 regions. If you have 3 points, you get 4 regions. Okay, good. Now just continue this process. Suppose you choose another point, 4 points. Again, randomly position, nothing special. I'm not choosing any special point. Just choose random points, generic points. So choose 4 generic points on a circle, and then connect all of them together. How many regions do we get now? 8 regions. So therefore, we get this table. 2 points give you 2 regions, 3 points give you 4 regions, 4 points give you 8 regions. Do you see the pattern? Okay, how many regions do you think we're going to get with 4 or 5 points? How many think it's going to be 9? How many think it's going to be 10? How many is, 10. How many think it's going to be 12? How many think it's going to be 16? Okay, majority of you think it's 16. Okay, indeed, if you do one more point and you connect them and you count, you see it's 16. So 2 points give you 2 regions, 3 points, 4 regions, 4 points, 8 regions, 5 points, 16 regions. Do you see the pattern? How many think is the pattern is that each time you add a point, you double the regions? Raise your hand. Okay, how many can explain this pattern? Why does it double each time you add a point? How many think the reason is simply the following? You're connecting 2 points and you get, each time you connect 2 points, the region is either to the left or to the right. So there's a factor of 2. So each time you get an extra factor of 2. How many think this is the correct reason? Okay, so this is the way we come up with hypotheses and explanations and come up with the law. So we come up with the idea that if you have 2 points, you get this, and each time you add a point, you get 16. So without even doing the next one, we know the answer. If you get 6 points, how many think is 32 regions? Raise your hand. Okay, so let's do it, just to convince ourselves. What? What? 31? How could that be? I'm miscounting probably. No, there's no miscount. You can count them if you want. 6 points is 31 regions. I'm sorry. The theory is false. Our experiments fooled us to come up with the theory. The theory we came up with was just wrong. And we did more experiments to cleanse our theory. We always do more experiments just to make sure we didn't make a mistake. And here, we did make a mistake. It looks such a nice pattern, though. You know, science goes by pattern. See, it's got funny patterns here. How come it be 31? What if we did 7 points? It's not 64. Well, it turns out to be 57. So in fact, you can figure out the full formula for it. The number of regions is 1 plus n choose 2 plus n choose 4. So it mimics x power law, like 2 to the power of n minus 1 for the up to n equals to 6, but at n equal to 6 and onwards, it doesn't work that way. So it's a polynomial growth, not exponential growth. Anyhow, so the main point here is that we cannot get too cocky about understanding. We really have to check our understanding. And sometimes we have to revise our paradigms. We might be making a mistake in our reasoning or our pictures, and we have to come up with the correct one. And this is the correct formula. I hope I have conveyed the power of simple mathematical ideas in the context of physics. Even the most advanced ideas in string theory have simple mathematical underpinning, just like the puzzles we have discussed today. Thank you for listening to my talk. And if you would like to see more of these puzzles, together with their solutions, if you wish, they're all in the book that I put out, Puzzles to Unravel the Universe. Thank you very much. I'm happy to take questions.
Hi, everyone. So I'm just going to jump in here quickly. I'm the admin, Miyako, for the ColumbiaDC School. I hope everyone enjoyed that question. You have tons of questions now. I'm going to lower everybody's hands so that we can have a clean start here, and then raise your hand in the by pushing the button if you have a question, and then I'll take the order, and then you can unmute yourself to ask your question. Video on is great, not necessary. And if you don't have video or audio, you can type your questions into the chat, and I will try and see some of those as well. So I think our first question that I saw was John, no last name. So John, it looks like you're also unmuted if you want to go first.
Hello, Professor. Thank you very much for a wonderful presentation.
Hello, thank you.
I have a question that touches on what you've discussed that's bothered me for a long time, and I'm a nuclear engineer, and that is I have an unshakable vision of the universe as a conventional explosion with a center radiating out into a vacuum. Can you explain a different, in layman's terms, model of the universe?
Yes. The universe does not have a center. And it's homogeneous everywhere. And you could say, well, where does it happen? It happens everywhere at the same time. So the explosion that you're talking about, the Big Bang. So, and so the analogy that is usually referred to is the following. You think about, it's hard to describe this in 3 dimensions. Our universe is 3-dimensional, but suppose we were a 2-dimensional universe. Suppose the space is only 2-dimensional. Then the good analogy would be that it's like we are living on a surface of a balloon. And when you say that the balloon is expanding, every point on the balloon is expanding, and there's no preferred center on the balloon. Well, there's a point in the center of the balloon, which is not part of your universe. I'm not talking about that. I'm talking about this 2-dimensional surface, which is our universe. And there is no preferred point. So every point is expanding at the same time. And if you go back, the explosion happened everywhere at the same point because all the points on the balloon are together at that point. So the 3-dimensional version of this, which is harder to draw, is the same story that we think Big Bang is about.
Thank you very much.
You're welcome.
Okay, let's do Vivian Moore next, and then Lionel Rivera, you'll be after Vivian.
Thank you. Thank you so much. That was really fun. I'm almost afraid to ask this question because I'm not a physicist at all, but my son was super interested in the double slit experiment. And so I just want to ask, it seemed like when you were talking about the light, you know, from how we see the different lights coming from one place and the, you know, the 3 and 5s and the
Yes.
odds, somehow that fits in. And when I read it, just like on Wikipedia or something, I thought, oh, that sort of sounds like that. And I mean, if you can at all say like, okay, no, that's not it at all, or simplistic explanation, maybe just set me straight on.
Yes, sure, I'll be telling you. So the thing I was telling you about is part of classical gravity. In other words, you solve Einstein's equation, there's no fuzziness of quantum mechanics, and you get 3, 5 images, etc. The double slit experiment is a quantum experiment. That means involves the interference pattern of particles and probabilistic aspects of quantum mechanics, the fuzziness of particles, which is different. So it's really different physics. So no, they are not related. So that's a bit confusing, but they are not related. One is having to do with quantum mechanics and the fuzziness at very tiny scales, but this is gigantic, you know, experiments involving, you know, galaxies and
right. But the double slit experiment still, like, I guess, is still unexplainable as to why it's still a mystery.
Well, in a sense, it is not. You know, in some ways,
okay.
quantum mechanics is always mysterious. But let me say it in a way which is not mysterious. Suppose you're like on a pond or on a pool, and suppose you put a kind of obstacle which divides the pool or pond to 2 different parts. And suppose you make 2 little holes, and you create a wave on one side, and what you see is that there are two little wavelets emerging from these little places, and these wavelets interfere with each other. So farther away, you see some kind of interference pattern, which is quite beautiful, but you know, interference is just coming from these 2 slits. What happened is you create one wave on one side, and that this one wave became split to 2 waves, and these waves interfere. This is what happens in quantum mechanics. A single particle splits to 2 waves because the particle is a wave, and passes through both slits at the same time and interferes with itself, and giving you this interference pattern. So at the level of waves and the analogy with waves is very intuitive. But the idea which is unintuitive is how could the particle split? So I say, for example, the electron passes through both slits at the same time. It's a real regular particle, like a classical particle, just goes either from slit A or B, not both. But since these are fuzzy, it could pass through both when they are close to each other. And this is what happens in quantum mechanics.
Okay, thank you. It sounds like it's not quite as mysterious as some people make it out to be. Thank you.
No, it's not mysterious. As long as you're willing to accept that electron can split to 2 and pass through both at the same time.
Thank you.
Okay, I do also just want to remind everybody you can order the book. We did send around the link in the email. Our next question is from Lionel Rivera. If you want to unmute yourself, you can ask your question.
Thank you, Professor. That was really, really fun and interesting. I just had a really general question, actually, about any thoughts you might have on the recent results regarding the muon, both at Fermilab, the magnetic moment experiments, and also at CERN regarding the asymmetrical degradation of beauty quarks into muons versus electrons.
Right. I mean, these are experiments. Sometimes we get things which are unexpected, like magnetic moment of muon and so on, which suggests that there's new physics coming up. And this is one of the experiments that they have seen in Fermilab, which doesn't seem to agree with the expected magnetic moment. But this is too early. And you see, these happen again and again in physics. And you know, there are certain things that we cannot be completely sure, and we have to check the experiment is done correctly, or our interpretation of the experiment is correct, and so on. So I would say I wouldn't read too much to it yet. It sounds like potentially interesting, but I wouldn't say it's a sure bet new discovery.
And just to follow up, is that partially based just on like the 40,000 to 1 probability, as opposed to like some different threshold that you might be more comfortable to seeing the certainty that it's not like a random result?
No, well, the 4,000 to 1 is a way you calculate it. If it was 4,000 to 1, I would not be saying this. I think that the way you calculate to come to that number is the question. So there are some systematics which go into that, and people may be ignoring. So I wouldn't rely too much on. Don't view that number as too strictly. So let me just give you another example. Some people had calculated before the experiment, based on some theory itself, predictions for the experiment that came out, and the experiment agrees with that prediction. It disagrees with the different predictions. So therefore, you say, wait a second. So it agrees with one prediction that people have made before the experiment was done, but disagrees with a different one. It said, yeah. So what was the other prediction based on that it disagrees with? Well, it was based on yet another experiment. So basically, we have two experiments which don't seem to be agreeing with each other in some form. And why and so on, we don't still quite understand. So I wouldn't read too much into it yet, but it's interesting and people, physicists are, of course, deeply studying to see what is really going on. We don't really know yet.
Okay, thank you.
You're welcome.
Okay, I don't see any more hands. We do have about 10 minutes left if anybody wants to jump in and ask a question. All right, Vivian, do you have a follow-up?
I did. Well, I have another question if the floor is free, but I'll defer. I know that Harvard has just created this new quantum science initiative, which sounds like incredibly exciting. I listened to the talk about it to the alum, and it sounds like, you know, the new 21st, the new revolution of the next 100 years could be in material science because and they're investing a lot of money in building and everything, and it just sounds super exciting. Just love to hear your thoughts.
Yes, I think it is actually. Many things are going on with this quantum aspects of physics. For example, quantum computers is one aspect of it, which many people are hoping will come to fruition and impact, you know, daily life. The power of quantum computers could revolutionize our lives. Now, when that will happen or how that will happen is still debatable, but clearly, the more we invest in this direction, the better chance we have to get to things like quantum computers. And, you know, quantum things in general give you new ideas, like new material can be based on them and so forth that people haven't thought about before. So there are many cool things that can come up from better study of quantum aspects of matter and realization of quantum nature of reality in materials and things around us. So I'm very much for this recent initiative at Harvard, and there are many other places that they're doing similar things. So I think it's a very timely thing to do.
If my son didn't have like the deep, he had an okay high school math background, is there some area in math that I think he's majoring in all the biogenetic stuff, but he's so interested in this, and I don't know, is there some area of math that he would focus on that would at least get him to the place where he needs to be for some of these more advanced physics classes? Is there some, like,
this is a high school, or which level are we talking?
Well, he's a rising sophomore at Harvard now.
At Harvard.
Yeah,
So
and
I would
he
say
likes
that
Math 1B, but I think he's going to need more to take real physics.
right. I think that, I mean, there are these like Math 1A, 1B kind of things, and also you can start there, of course, but you can then take more things like algebra and this and that. But you know, many aspects of science don't necessarily need deep math. I mean, you of course need calculus and things, but there's one thing to be, you know, the detailed theoretical physicist doing things like string theory that I'm doing, which needs a lot of math. But then there are a lot of cool stuff which don't need that much math. You know, experiments, and you create, you know, equipments which probes into these theories that we want to probe. So the different facets of science, and not all of them need a lot of math. So so I would say that it really depends on what kind of interest your son might have. But I think their opportunities are open, and you know, can knock at the doors of people and try to see what they're doing and trying to see which one, if any of them, interests them, and not necessarily worry about the math so much.
Thank you. I see other people have their hands raised. Thank you so much.
Sure.
Okay, let's go to Tom from the Harvard Club.
Yeah, Professor, wonderful, wonderful talk. You remind me of a professor I had at Harvard, Professor Ramsey, and
oh yeah.
his ability to create fascinating analogies that explain things in a remarkably clear way. I'm wondering, since you focus on string theory, all the discussion of cold dark matter, and I was wading through an article that I found very difficult to understand, although some of what you said helped. The idea of the gravitational lensing through galactic clusters. It turns out the mass distribution is not what the cold dark matter mass distribution has to be in galaxies spread out to explain the velocities of things. So what do you think is going on? Where is your speculation?
Well, I'm not sure exactly which one you're referring to, but I think that, I mean, the dark matter is one of the big mysteries for us. We don't really know what it's made of. Cold dark matter is one model for it, and what that cold dark matter signifies exactly, we don't know. The distribution of the cold dark matter and the evolution of it, there are some theories about them and how they're distributed in our galaxies and bigger superclusters and all that. There are some theories that we have some distribution predictions and so on, but I wouldn't say it's a point where we have a solid, completely understanding of them. So there are many things that people are trying to understand in that context as well. So there could be puzzles related to that, but the specific one that you're talking about, probably I'm not sure which one you're referring
to. Okay, we had a question come in from Glenn Homan, and I think we probably don't have enough time for you to go too in depth here, but he asked you to explain how quantum computing works.
Ah, that's a good one. Well, it's hard to give a clear exposition of it without, you know, having the quantum background, but let me try this anyhow. So a classical computer is very boring. It's either made of things like 1 and 0, circuits on and off. Like, it's very kind of like not nuanced, kind of like 1 0 1 0. It's not like us. We kind of, when we talk and so on, we say something that could have a lot of meanings and so on. Quantum mechanics is more like us. Like, it's not just a 0 and a 1. So what does that mean? Well, for example, if you have an electron, it could be spin up or spin down. But in quantum mechanics, it could be made of both spin up and spin down at the same time. So it's an admixture of different states at the same time, just like the electron, which was going through these two slits at the same time. So this amount of how much is going through one versus the other one gives you a continuous parameter. So it gives you a degree of freedom, which is not just 0 or 1, but a kind of a number, if you wish, between 0 and 1. It's kind of a fuzziness. So if something is not just 0 and 1, just any number between 0 and 1, it's much more degrees of freedom, much more choices. So quantum computer is taking advantage of that. That's the basic idea. And how you manipulate that is using the laws of quantum mechanics. How you make these circuits is using quantum mechanics. That's the very basic aspects. But there are things that people have had challenges with, and has to do with errors that computers typically get you. And so you have to find a mechanism to get rid of errors, And there are these codes that people talk about called, for example, quantum error correction codes and other things that try to fix these up when you have some errors. And implementing on the experimental side to have noise and experimental noise, which messes up the quantum purity, are tough challenges for quantum computers.
Okay, great. I see Wade had his video on, so if you want to ask your question, Wade, we have about 5 minutes, and if we can get to Lionel second, we'll do that next.
Great, thanks. I know there's been a lot of effort that's gone to try to unify the fundamental forces. My question is there a theoretical reason to think that we know that we know there are no more theoretical forces, or is it just that these are the ones we have discovered so far?
It is more like these are the ones we have discovered so far. It's very possible that they have other forces. In fact, unification of forces predict that there are other forces. And so we believe that if you go to higher energies or higher temperatures, you'll discover new forces.
Great. Okay, and last question will go to Lionel.
Yeah, mine was just very general, since at least when I was thinking about it, the floor was open. So obviously, I don't know if the professor already answered it, but basically just very open-ended. Professor, what are you most excited about, either on the experimental or theoretical front, personally, in physics?
Well, right now I'm myself working on a program called the Swampland program. The Swampland program is telling us what are the things that cannot happen. And it turns out that in string theory, there are many things that you might think are okay, but actually never occur, never appear in string theory. Certain particles never can appear, certain forces can never appear. Why? Trying to understand that is one of the things that I'm really excited about. One of the applications of it is to the stability of our universe. So for example, we're beginning to see that our universe, because it has dark energy, is going to decay away. We're not going to stay forever. I don't mean live just, unfortunately, our lives. I mean, the whole universe is going to disappear. So this is not just, me and you not being around. The whole galaxy will not be around. There's nothing around. There'll be completely different laws taking over. When does that happen? We don't exactly know. We have some predictions. Coming up with models which try to come up with how, the mechanism, why, where, etc. is what's most fascinating me. That's one of the areas, the future of our universe. The other one is the past. Where did we come from? And again, it turns out things we are learning in string theory in this context is teaching us new information, that perhaps we emerged from a different universe. And the Big Bang was not a point necessarily, but it was the point that we recognize as the beginning of our universe. But before that, there was this other universe. And that other universe was made of completely different degrees of freedom than ours. And from the different beginning, we emerged. And how this happens involves symmetries in string theory, like dualities I was telling you about, which involves inversion symmetries. Like if you shrink the length of a universe, it turns out equivalently to growing the size. So there's a symmetry, R goes to 1 over R. So when you make R very small, it's as if you're making it big. And these kind of dualities will tell you that the universe, when it's shrinking, is actually equivalent to expanding universe. And so that could have been a beginning of the end of a different universe, which was the beginning of our current epoch of the universe. Anyhow, so these are the kind of things I'm mostly fascinated by.
Well, I'm really glad I asked, because your answer officially blew my mind. So thank you.
Thank you for asking.
All right, thank you everyone so much for attending tonight. We hope you enjoyed the talk. We will be posting the recording on Columbia's YouTube channel tomorrow, so you can take it, look at it, send it to your friends and family. Professor, any closing thoughts for us?
No, I just very much enjoyed the talk here and your questions, and hope you have a safe pre-COVID era, and hopefully we'll enter the good post-COVID era soon enough. So thank you, and hope to see you maybe in person in the next such occasion. Thank you.